So, electrochemical cells. The ones we were looking at yesterday, and if somebody wants to erase Bohr and Thomson, you can, if it's going to bug you.
I read one yesterday. I'm very excited about it.
Just take notes on a piece of paper. It'll be okay. All right. So, yesterday what we were looking at were galvanic or voltaic cells, aka batteries. So, they make electricity. You could technically make them out of a piece of fruit. My juniors, we did that in lab last year. It was pretty funny. We literally stuck pieces of metal in fruit and measured the voltage.
Yeah, I
had a parent that's calling, trying to get her son to access.
He has to call UT.
She did, and they didn't. They said to call.
Okay, to call who?
I don't hear us or something.
Which you have no control over it. I'll talk to him later, because, yeah, you have no control over their...
I told the parent I'd call back, but...
I mean, you can try calling UT and see if they'll tell you anything, but
Yeah, I doubt it. But what is this?
It's an online homework system.
You can fundraise.
And...
Is there any way to make him a different logon?
He can make a different logon, that's probably... I would call the parent back and tell her to have him make a different ID
And what's the web page?
quest.cns.utexas.edu. My suggestion is have him leave his middle initial out this time.
Okay, and is there a, does he need a code?
It's on a handout that's, like the directions are all on a handout that are on my Google Classroom, which, yeah. I've had more issues this year with people just like managing to completely
Get mixed up.
Yeah, it's been bad.
All right, thank you.
Yes. So, getting back to this. So, things that are going to make batteries are what we're going to start with. The first part of this, my juniors have seen. There's going to be a bit at the end of today probably that you have not. So anytime we see voltaic or galvanic cells, they're ones that are actually going to make electricity. Electrolytic cells, which we'll talk about probably Thursday, are things that don't want to happen the way you've got them set up, and you've got to actually put electricity into it to make it work. But this is how you do like electroplating and such. All right, anytime we're doing electrochemistry, we're going to be doing redox reactions, so remember all our basic redox things. We are going to have to look at how many electrons are coming from each side, because that will affect how we balance things. All right, so anytime we're doing an electrochemical cell, we're always going to put the anode on the left and the cathode on the right, and electrons always flow from anode to cathode. If it's galvanic, it's spontaneous, it's going to happen on its own. You'll sometimes see it referred to as thermodynamically favorable. That is what most people say these days instead of spontaneous or not. So you're going to have oxidation happen on one side, reduction happen on the other. The electrolytic cells are going to be thermodynamically unfavorable. Those don't want to happen. You've got to force them to happen in some way. Like I said, today we're going to focus on galvanic. So anode is where oxidation happens. Pair your vowels. Cathode is where reduction occurs. Pair your consonants. So if you've got metals, the anode is going to lose mass, the cathode is going to gain mass. Because in the, like here when we're doing zinc, if zinc undergoes oxidation, are you going to start at metal and go to ions, or start at ions and go to metal? Metal and go to ions. So zinc is becoming zinc Ions, where are those going to be? In the solution. So you're dissolving some of your zinc while this happens. The copper, if it's being reduced, is going to start as our ions and go to our metal. So your piece of metal is going to gain mass as you pull more ions out of solution and plate them onto your electrode. Anytime it talks about an inert electrode, it means it's not doing anything. If you're not doing, like if something's not a metal, or their example is if you're going from Fe3 to Fe2. Anytime you see a platinum electrode or a graphite electrode, you're just doing an inert electrode. It's not directly related to what's going on. Salt bridges have to be there, A, to complete the circuit, and B, to balance charge. Be warned. AP likes asking about what's the purpose of the salt bridge, or they'll give you a cell that's missing the salt bridge, meaning like, what's missing from this setup so that it's not working? It's just like a glass tube filled with Jello with electrolytes, roughly. Okay, strictly speaking, it's agar and not Jello, but Jello with electrolytes would probably work. I haven't done it before, but I kind of want to try it out. You can do simpler things than that. When we do lab, hopefully Friday, I might move it to Monday, we'll see. But we'll actually do a lab where we're doing galvanic cells. A paper towel that's been wet with a salt solution will also work. Had a friend one time who apparently they were bored one night and used like paper towel wet with salt water and like aluminum foil. Like they were making their own galvanic cells. There may have been alcohol involved. It was apparently very strange. Yes.
Wait, so by salt like sodium chloride.
It doesn't have to be sodium chloride. Nitrates are typically common. Because what's the problem with using sodium chloride when we're doing reactions with metals? What are nitrates always? What about chlorides? So you're going to have some precipitate issues and some solubility issues with your chlorides. So nitrates are generally the safest. So like the lab we're doing with galvanic cells, I think we use potassium nitrate, because then you're not going to end up with any solubility issues. Electrons are always going to flow anode to cathode, also known as left to right. Yeah, which is nice. The one thing you have to watch out for is check to make sure it's set up correctly before you say that. Every once in a while, AP will ask you a question so if you set it up correctly, all of this is true for a positive voltage. Positive voltage means it's set up correctly. If you've got an AP question where you get a negative voltage, it means all of this is backwards. And you guys saw that in the simulation yesterday. If you flipped around left to right, you just got the same voltage but negative. So these things are true if you've got a positive voltage. If you had negative voltage, it's backwards. So pay attention to that.
So is this how like actual real batteries work?
Roughly, so in real batteries, among other things, you're less likely to have actual liquids involved because that would be messy. The exception being your car battery. Your car battery is full of sulfuric acid, so it works. Car batteries are actually one of the more simple kind of batteries because you actually have your electrodes in there and you can refill your solution. Most batteries are done with more of a dry cell, so you've got sort of like a paste together, so things happen. One of the reasons that you can recharge some batteries is because electrolytic means you force electricity into it and it goes backwards. So if it's rechargeable, you can do that. If it's not rechargeable, going backwards, one of your reactions tends to make hydrogen gas and explode. So if anybody that's ever was like, hey, I wonder what happens if I try and recharge these non-rechargeable batteries, explosion. Not usually a dramatic one, but explosion. Alright, and these are just some mnemonics to help you remember. Anox, oxidation at the anode. Red cat, reduction at the cathode. Fat cat is to help you remember from anode to cathode.
Adorable. I like that.
Also remember the cathode should be positive if we're making a battery. Anode is negative. The nice thing is, AP doesn't ask about this anymore. So AP should not ask you about whether that's the positive terminal or the negative terminal, because frankly, when you do electrolytic, it switches around, and it's all kind of convention anyway. Alright, and we talked about the salt bridge. EPA is the other thing. That's, again, with the electrolytic cell, you have a positive anode. You aren't going to be asked about the signs on the cathode and the anode anymore. It's not a bad thing to remember, but... Alright, so galvanic cells, all of these are going to involve redox reactions. So we want to look at what redox reactions are happening. So in this, we've got permanganate ion adding to iron 2 gives us manganese 2 and iron 3. So which is the easier one to make a judgment about what's being oxidized and what's being reduced? So iron is being oxidized. So iron is being oxidized, and so then reduced has to be manganese. Okay? So let's balance this real quick to make sure that we can, because we haven't balanced a lot of redox reactions, and that's really important this unit. So my reduction half reaction, MnO4, is going to go to what? Mn2 plus, and we'll deal with doing the rest of it in a second. Then my oxidation is going to be Fe2 plus going, that's supposed to be an arrow, not a plus, going to Fe3 plus. Alright, let's balance the second one first because it's easier. Do my elements balance? What doesn't balance? Charge. So what do I need to do to balance charge? To which side? To the right-hand side. Okay? Up here, do my manganese balance? What doesn't balance? What can I add to balance oxygen? Water. Thank you. How many waters do I need to add to balance my oxygen? 4. Okay. So then, what do I do to balance my hydrogen? I can't balance water with water. What? That's to balance charge. What other form can I put hydrogen in?
Gas.
We already tried gas. You're closer. That's only if we're in base, and we frankly don't do base that much. So when we're writing a net ionic equation, which part of hydrochloric acid would we actually write? H. With what charge? Plus. You add H pluses to balance your hydrogen. And how many H pluses? Yeah, we talked about this at the very end of last unit, but we've slept since then. 8 H pluses. Alright? And then last order of business is balance charge. So what is currently my total charge on my reactant side? 7. Because I have 8 pluses plus 1 minus. And my product side, I currently have 2 plus. So how many electrons do I need to add, and where do I need to add them? 5 to the left side. Okay? So now, I need to add my 2 reactions together. So we'll move this up here. but I need my electrons to cancel out. So which one of these can I multiply something by to make my electrons cancel?
5.
Which one?
Top 5. Gibbs 5 times the electron.
So which one do I need to multiply by 5? The bottom one. Okay? So what's going to happen to my electrons? They cancel out. Then I'm going to have 8H plus MnO4 minus plus how many Fe2s? 5. Gives us 5 Fe3s plus Mn2 plus here, I'll move that up so it's all in one. Plus my 4H2O. Okay? So if I put them in the same container, the reaction would just happen. You couldn't do anything with it. By separating it out, then you can get an actual flow of charge, which is why you can get electricity out of it. 4H2Os. Sorry. I dropped the coefficient. So it has to be something that can make electricity, and you have to separate it out and set it up right. The other thing you'll see sometimes instead of a salt bridge is a porous disc. These are a little less common because you have to have 2 beakers that have been put together with something with a porous disc. And they're kind of fragile. But it's going to be the same. You can actually get ions flowing between the porous disc. All right, cell potential we looked at yesterday. It is referred to by all sorts of things. Just pay attention. It's going to measure your voltage. You can measure it with a voltmeter. So each thing has a standard potential. We measure it against hydrogen. Hydrogen has a assigned value of 0, and then you work from there. And so you'll have a table of E cell for each half reaction. This is going to use 1 molar solutions of salts. We're not going to deal with significantly what happens when you change concentrations. We'll talk about it a little qualitatively. We're not going to do the math on it. So it's going to talk about the Nernst equation. Don't worry about the Nernst equation. It is no longer on the test. All right. So you will have happy little tables like this. These are standard reduction potentials. So they are actually written as reduction. The higher it is toward this side, the more likely it is to get reduced. The lower it is toward this side, the more likely it is to get oxidized. I can't spell oxidized, apparently. We're just going to say get ox. So, the higher it is on the list, more likely to get oxidized. Lower, it's going to get, reduced over here, oxidized over here. So, lithium and fluorine would make a fantastic, fantastic battery. At least from an electronic standpoint. I need to find, this is reminding me, I need to find an article I found the last time I taught AP. Some researchers at I think MIT were trying to build a better battery and accidentally found a really good way to smelt metal. Like, make pure metal out of a metal compound. It was not what they were going for at all, but I think they were probably grad students, so it was less good grade and more published to paper, but yeah. All right. So when we're trying to find our E cell, you work with it exactly as it is on the charge. On the chart, you'll flip it. If it's the oxidized one gets flipped and you change the sign. And then you can balance it. Don't change your voltage values. Your voltage values never change from what's on the table, even if you have to multiply things because of number of electrons. All right. Our other way, if you don't want to deal with flipping your signs, E cell. What did we end up finding yesterday got us the right value for our E cell? Cathode minus anode. So if you do right minus left. This one's probably a little easier to work with. Okay, and this is one equation you actually have to memorize for the AP test. They do not provide any form of this equation on the reference page. But yeah, cathode minus anode is what we want to do. So here, we've got aluminum plus magnesium gives us aluminum and magnesium ions. We want to give the balanced cell reaction and calculate E for the cell. So let's actually do E for the cell first, because do you need to balance the reaction to get E cell? No. But to do, the one thing we do have to figure out is what's going to be our cathode and what's going to be our anode. So, should cathode be my oxidation or my reduction? Reduction. Who's being reduced? Aluminum. Because going from +3 to 0. And then anode has to then be my magnesium. So we go back up to our table. And we've got to find aluminum and magnesium. So let's see. Here's my magnesium. There we go. So my cathode is my aluminum. What was my value for my aluminum? -1.66 minus, what was my magnesium? 27? 37, okay. So then my E cell is going to be and the table also gives us confirmation that aluminum should be reduced because which one was higher on the table? Aluminum. And higher on the table means it should be reduced. But we also have the balanced equation. But if it doesn't give you the equation, that's you can judge. Higher on the table should be reduced as long as it's a galvanic cell. Because you're trying to get a positive value. The higher up, right. The higher up is more positive, so you've got to make sure you're getting a positive value in the end. All right, I don't have said more complete table. So we want to calculate the voltage for the galvanic cell that would utilize silver metal and involve iron 2 ion and iron 3 ion. We want to draw the diagram and label it completely. So which do we want to do first? Calculate our voltage or draw our diagram? Draw the diagram, okay. And how do I want to connect the two halves of my cell? Salt bridge. Nobody mock Miss Copeland's art skills. All right, what else do I need in my cell? I need solution. Because what happens if you don't put solution in?
Nothing happens.
Nothing! Because all of y'all saw that yesterday in the simulation at some point. Alright, what else do I need in each side? Electrodes. So, are both of them going to have... So what's the metal going to be on the silver side? Silver. What's the metal going to be on the iron side? What am I doing with my iron? So is iron metal ever involved in this reaction? No. So what did it tell us to use if we're not trying to go between the ion and the metal? It was a special type of electrode. Inert. And so what are the examples of inert electrodes? Graphite's cheap, and then platinum's expensive. Which one do we want to use? Platinum, because we're not buying anything here. So before we finish this out, we do have to decide what's being oxidized and what's being reduced. So go back up to our table. So we're looking for silver.
Silver is way.
Be careful.
Just
So if you look at the silver that's way, way high,
oh,
it's 2 plus to 1 plus. We're looking for one that involves silver metal.
okay,
Yeah.
So silver's there, and then we need iron 2, iron 3, which is going to be right below there. So which one of these is actually going to be reduced? Silver, because it's a little bit higher. So silver is going to be my cathode. Iron's going to be, well, the iron cell is going to be my anode. Where do I put my anode? Where do I put my cathode?
Anode's on the left.
Anode's on the left. So which one's going to be on the left? The iron. And I'm going to have a platinum electrode. And then over here is going to be my silver. And I'm going to have the silver electrode. Just believe me, that's an AG and not an HG. Okay. And then, how am I going to know if it's doing anything? You need a voltmeter.
Okay.
And then what else do I need?
Wires.
I need wires. Because otherwise it's doing nothing. So there's my cell. Alright, so we said we would need to do cathode minus anode. What was my voltage for silver? .8 minus my iron, which was, and so my E cell is then going to be 0.03 volts. So it is technically thermodynamically favorable, but not by a lot. Alright. So now there's a little bit we want to look at that nobody has seen before. Sorry. Alright, so one of the equations you have to deal with in this is going to be this one. Delta G equals negative NFE. We haven't really talked about delta G yet. The things you need to know about delta G. Negative delta G is favorable. Positive delta, that's a delta, not whatever else that was going to be, is not. And one of the ways to remember this is we just said if the reaction wants to happen, what should my E cell be? Positive or negative? Positive. If I put a positive number here, my delta G is going to be Negative. Because N's a counting number and F's a constant. So delta G is my free energy, sometimes referred to as Gibbs free energy, unrelated to the guy from NCIS. N is number of electrons, and then F is Faraday's constant, which is right here. Delta G equals negative NFE is on here. The F, they go ahead and give you the full F, but usually rounding to 96,500 will get you there. My juniors, you have seen F before. We just didn't call it that because we weren't using it in this context. Yeah, but those are actually the easier ones because then it's just most of those are just two-dimensional analysis. So this is part of the reason why a negative E cell is not good, a positive E cell is good, because you'll get the appropriate delta G. So using our standard reduction potential tables, we want to calculate delta G for this reaction. So the first thing we need to do, and this part is a little easier, because delta G is negative N. How many electrons have to get transferred for this reaction to happen? What's happening to my copper? From 2 to 0. And iron is going from
0 to 2.
So how many electrons have to move? 2. In ones where it's not an equal number going each way, you have to balance things. And then F is my 96,485 times, now I've got to calculate my E cell. So copper is getting reduced, iron is getting oxidized. Let's go find my copper and my iron. And make sure we can find the appropriate ones for each.
It's the negative 0.44 for the.
Yep. So here's my iron. Oh, there it is. Nope, nope.
It's going 2 to 1.
Yeah, it's 2 to 1.
Yeah, I need 2 to 0. Oh, there we go. It's the 0.34.
Yeah, I was just about to say.
There we go. Okay. So my E, you'll have to tell me my voltages again. What's being reduced? Copper, so start with coppers. 0.34 minus, what was my iron? So you guys can flip back a little more easily than I can.
Negative 0.44.
Negative 0.44. And so what do I get when I do that? 0.78, and then I multiply my numbers together. But if all it actually asks you in the end is not so much what the value for delta G is, but based on delta G, is this favorable or unfavorable? Yeah, because if I've got a negative times a positive times a positive times a positive, then my overall answer is going to be
Negative.
And negative delta G means favorable or not?
Favorable.
Favorable. So we know we've got a negative delta G, therefore favorable. Alright. Then it wants us to do, using the standard reduction potential tables, can we use nitric acid to dissolve gold metal and form an gold 3 solution? So let's look back up real quick. We won't even probably have to do the math. Alright. So, where's my... What do I know hydrogen's going to be? 0, because that's my standard hydrogen electrode. And then where is gold to gold 3?
1.5.
Okay. Well, that's gold 3 to gold. And so, which one of these is actually going to get reduced? The gold. So, given this combination of things, can gold be my oxidation? No, it can't be. It can't go from 0 to 3 with something that's considerably lower on the list. So, can I dissolve gold in nitric acid? No. Alright. Okay, and so the only thing we're going to talk about with dependence of cell potential on concentration, when we're assuming standard metal kind of cells, which of my reactions is making more ions? Yep, let's not write in highlighter. So which side is going to make more ions? My reduction or my oxidation? Assuming metals. Oxidation, because I'm going to go from metal to the higher charged ion. So that's oxidation, which means it's also my anode or my cathode. Anode. So if I start with a higher concentration in that cell, is it going to make life easier or harder? Do we think? If the point of the reaction is to make ions. If I'm trying to make ions, do I want to start with more ions or fewer ions? Fewer. So high concentration will give me a lower voltage. Low will give me higher. Because we'll talk about this a lot more in equilibrium. But if you're trying to make ions and there's already a bunch of ions there, then it makes it harder for the reaction to go. So the opposite's going to be true on reduction. Needs more ions. So do I want to start with a high concentration or a low concentration?
You want to start with the
Right. So higher concentration is going to give higher voltage. And again, we will talk about this in more detail when we get to equilibrium. But just whichever side is making ions, you want to start out with less. Whichever side needs the ions, start with more, because you'll have more to work with. All right. We are not doing Nernst equation. Do not worry about Nernst equation. We don't really do concentration cells. Don't worry about that. All right. So another way we can use delta G is delta G equals what is semi-affectionately referred to as rat link. RT natural log of K. That's a lot less fun, yes. So the biggest thing is K is going to be your equilibrium constant. You don't really have to know most of the ways to calculate it yet, but the reason this is important is you can do negative NFE equals negative RT natural log of K. So if it tells you your equilibrium constant, you can calculate your E. If you know your E, you can calculate your K. And that's the main way this is going to show up at this point. R, in this case, is always your 8.31, because that's going to be joules per mole Kelvin. You need energy involved in that. Friendly reminder, make sure you check your pressure units before you pick your R's. We had several people using inappropriate R's on the last test. Remember that torr and millimeters of mercury are the same thing. So we are about out of time for notes today. So we're going to go ahead and stop here. We'll pick up on exercise 8 tomorrow.